We are delighted to have Emily Dryden, who will talk about, will give a talk entitled, Can a convex polygonal domain be Steklov isospectral to a smooth domain? So we look forward to hearing the answer. So over to you.
Thank you. I'd like to thank the organizers for the invitation. So far, it's a great place to work, so I'm delighted to be here. So what I want to talk about today are some inverse spectral results. Okay, so the question is, if we have some domain, we're going to mostly call it omega. Okay, so I will just be in R2 today, no higher dimensions. So if we have some domain omega contained in R2, so this is some bounded open set. And I will be talking about a couple of different operators, but the question is really, from the spectrum of some operator, what can you tell me about the geometry of that domain omega? Okay, so that's our theme today with some particular questions. So this is asking, is omega uniquely determined by its eigenvalues? That's my ideal, that's my goal. It won't always happen, right? Okay, so some history to sort of motivate. You'll notice Steklov is in the title, but just to motivate some of those Steklov results. I want to talk about some previous work for the Dirichlet-Laplacian, and these are in a certain order. It's not chronological. The order might seem a bit mysterious, but it might become clear as we go through the talk why I chose that order. Okay, so what are some things we can hear? In other words, in what situations do the eigenvalues of this Laplacian determine something about the geometry? Well, for example, triangles are great. Okay, so we can hear triangles. So in other words, if I give you a collection of all triangles and I listen to its spectrum, I can tell you which triangle you have. Okay. This is a result. It's done by a couple different people. It was done. So within the collection we are in the collection of triangles to start with. So this was proved using wave trace by D'Urso in 1990. And then in 2013 using a heat approach by Grieser and Verona. So yes, this is a triangle among all triangles. Okay, so if we're looking at the collection of triangles, we can tell the triangles apart.
Did she ever publish it?
No, it's just in the thesis, which is hard to get. Can everybody see the top if I write here? Yes, okay. Okay, so we also have more recently in 2022, oh, sorry. And the result that they have is actually slightly more general than this. It's about semi-regular polygons, but for today, let's just think about regular polygons. So regular polygons among all convex, piecewise smooth planar domains. Okay, so if you're in the collection of convex planar domains, they've got smooth boundary. You can hear the regular polygons. All right, so that's a little bit more recent. I'm going to shorten some of these. So in 2016, so for shorthand, Liu and Rowlett showed that you can hear corners. Okay, so back to what's the context. So if you are looking among all domains, they have Lipschitz boundary, and you've got a piecewise smooth Lipschitz boundary and fixed genus, you can tell whether it's smooth or not. Okay, so you can hear whether there are corners. Okay, so one more. So earlier this year, preprint posted on the archive, Louis and Schur. You can hear if you have straight sides. So again, what are we looking in? We're assuming that we can have curvilinear polygons, but if we have one that has potentially curved edges and it has the same spectrum as one with just straight sides, the polygon you might think about, it also has to have straight sides. Okay, so these are some, classes within which we can hear, and then geometric features that we can hear based on the spectrum of the Dirichlet-Laplacian. Okay? All the sides have to be straight. The other one has to have all the sides straight. Okay? And this was, I mentioned here we had a wave-based proof, wave trace, heat trace. Here, this was heat. Okay? Okay, so the tools tend to be heat and wave trace, heat invariance, wave invariance. Today we're going to see what happens for a different operator, and we're going to see a different kind of tool. Okay, there have certainly been heat things done for Steklov, but that's not going to be my focus today. Okay, so we're trying to get similar results with different tools. All right, so here I'm going to switch to Steklov. Any other questions on the history?
Yeah, all of these results require to know all the spectrum, or if you know some infinite number of eigenvalues?
So typically they're based on, an asymptotic expansion, small time asymptotic expansion of the heat. So all, right? I'm trying to think. Yep, that one was all. Yep, all of them.
So, what is the most general statement that you believe is true in this? Is there like a...
You mean in terms of spectral determination?
Yeah,
For planar domains? I mean, certainly it's not true that you can always go backwards, right? So how much of the geometry can you hear? To me, I don't think... I think that's probably pretty general if you're thinking about piecewise smooth planar domains. There might be other interesting classes, right? So it's hard to say, I guess, a general statement.
Not determination of the angles on the...
I don't expect that.
Here's the result of Veldich and with that name, that if you have a symmetry in the real analytic linear spectrum.
Hazari and Zeldich, yeah. So certain symmetry, but in general. Okay, so let's move to the Steklov setting. Okay. Okay, so I want my functions to be harmonic in my domain, and I want the normal derivative along the boundary to be equal to sigma times my function, right? So notice the spectral parameter here is seeing the boundary, right, which is different, but it might give you hope that we'll be able to recover geometric features of the boundary, right, since the eigenvalues seem to really be dependent on this boundary, okay? So hence the title, right? We're hoping to figure things out about the boundary. You can think of these eigenvalues as being related to the characteristic value, the frequencies of vibration if all the mass of your domain is concentrated along the boundary, Okay, so I might still use the word here just to mean what does the spectrum tell me about the geometry. Okay, so one thing we can do is we can hear perimeter. Okay, this follows from vial asymptotics, which follows from work by Hormander. It's also some heat invariance from Polterovich and Schur from 2015 also give it to you. So either way, you get the perimeter. So there's some geometric quantity that we're able to recover. But that's kind of where things stop.
From what data do you recover this signal?
From the eigenvalue data, you can get heat invariance. And from those heat invariants, you get the perimeter. You can also do it from a Weyl law. I like heat invariance. So yeah, the sigmas. So hearing here means from those sigmas. Those are your spectral data.
And here the perimeter is the length.
Yes. Yeah, not where it's length. Thank you. Okay? Okay. But that's kind of where our usual heat and wave invariance, well, heat invariance stop giving us what I would call helpful information. Others may disagree. So we need a new tool. And the new tool we're going to use is something called the characteristic polynomial. This was introduced and then developed in a series of 3 papers by Levitin, Parnofsky, Polterovich, and Schur, and then Krimsky was added on the 3rd one. Okay, so maybe with this talk, I'm setting a record for the number of names that get attached to each theorem. I don't know. So in 2021, they showed that the characteristic polynomial P omega of t can be reconstructed algorithmically from the Steklov spectrum. Okay, so you have this. This is for curvilinear. Yeah, so we allow curvilinear. I don't care if the edges are curves or straight, but can be reconstructed algorithmically from the Steklov spectrum. Okay, of omega, if you like. I'm going to. Yeah. So before introducing it, because it doesn't look especially nice, I wanted to give you motivation to care. Okay. We're going to go through it. We're actually going to compute it in 2 simple examples so that you get a better sense for it, because it looks rather complicated the first time you see it. Okay. But the idea is, okay, so this tells us that Steklov spectrum will tell us P omega of t. And the question is, there enough geometric information encoded in P omega of t to determine omega? Okay, so what is P omega of t? Okay, we'll start with a triangle. So I have to be careful about my labels. And I will be a little sloppy. L1 is both the label on the side and the length of that side. Alpha 1 is both the measure of the angle and the label on the angle. Just humor me. So here, I'm drawing it for a triangle, but we have some vector of edge lengths. We have some vector of angles. Okay. We also have a third ingredient, Xi, and this is a vector of plus and minus ones. Okay, so we have some triangle, length vector, angle vector, and Xi for a general n-gon, but that's a lot to draw. Okay. Okay, so how do we find this p omega? Well, I'm going to write it down. Okay, so easy enough, right? 1/2 the sum of over all these possible X's. A Xi, I have not told you what that is yet. Cosine, absolute value of Xi dot LT minus this product of sine. So let me tell you what AC is. Okay, so we take everywhere where we switch, remember this is just a vector of plus and minus ones, everywhere we switch sign, we're going to take the product of cosine pi squared over 2 alpha j. Doesn't look very intuitive, perhaps. Let's compute one. Okay, so let's do an example. And this is an audience participation part of the talk, so I'm going to ask you to help me compute just to make sure you're, awake and following and all those things.
What is the characteristic polynomial? This is a statement that something defined in a completely different way would look like this.
So where does this come from? So they have many different ideas that go into developing this. They have these vertex, so the reason you might say this does not look like a characteristic polynomial, right? It's a polynomial in T. There are these transform matrices defined at the vertices. Eventually from that, those give you information that are in these things called quasi-eigenvalues. And then they show that these it's over 100 pages, so, but these quasi-eigenvalues are related to the spectrum. In the series of 3 papers, there's a lot in there.
What does omega have to do with this? Is
Right.
omega a polygon?
So omega here is a curvilinear polygon. We're going to look at it in the situation of a triangle, just to make this a little clearer.
It is a polygon.
It is a polygon, curvilinear, so the sides could be, and also, it works for a smooth domain. What comes out, I will tell you a little bit later, but the definition, so if you have something smooth, and you can also think about when X's don't change sign, what happens, right? So I have to tell you a little bit of nuance here. We will get there. Okay, so let's do an example. So we're going to have 2 triangles. They're each going to have perimeter 1. Okay, and alpha 1, it turns out we don't need to worry about the lengths. Alpha 1 is pi over 7, pi over 63. Exactly the triangle you would first think of, right? Pi over 7, pi over 63, 53, pi over 63, and alpha 2 is has angles pi over 9, pi over 21, and 53 pi over 63. Sure. Okay, let's compute. So for T1, let's just think about T1. So what are the contributions to the characteristic polynomial for T1? So this is a vector. If you want, I can, this is my vector of length. So this is alpha 1, alpha 2, and alpha 3 as in my picture. This one goes with triangle 1, this one goes with triangle 2. I agree. The notation is not the best. Okay, so let's think about what are C, HC, and C dot L. Those are all ingredients in this characteristic polynomial. So let's look at those first, and then we'll put it together and get the characteristic polynomial. Okay, so one C that you might reasonably think about what if you took plus, 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 or minus, minus, minus? Okay, those C's can happen. But then what is AC? Because there is no change, right? In the situation where there is no change, AC is defined to be 1. Okay, so 1. What is C dot L? 1, because it's just the perimeter, right? Okay, so that one was not too bad. Let's do a different one. Let's change the first sign. So -1, 1, 1, or 1, -1, -1. I claim those are equivalent. Okay, we can come back to that in a second. So where do my switches occur, right? That's what's coming into AC. So my switches occur from 1 to 2 and 3 to 1, right? In both of these, 1 to 2, 3 to 1. Okay, so looking at my triangle, as I switch from 1 to 2, I'm picking up something about alpha 1. As I switch from 3 to 1, I'm picking up something about alpha 3. Okay, so alpha 1 and alpha 3 are what go in my alpha j here. Okay, so this is cosine pi squared over 2, and alpha 1 is pi over 7. (53 pi). Okay, what does that equal? Anybody brave? 0. Right, okay, so yeah, 7 pi over 2 right here. So that's 0. Okay, so I don't need to care about this because my AXCs are multiplied by that term, but AXC is 0. All right, I'll give you one more. So what if we have 1, 1, -1, or -1, -1, 1? My switches happen between 2 and 3 and 3 and 1. Okay, so this time I'm picking up alpha 2. And alpha 3 again. See, it's 0 again, right? Because alpha 2, you can't see it, but alpha 2 pi over 63, right? That's another angle that seems to give us 0. Okay, so we don't have to worry about these. Okay, so some things to notice here. How many times is the sign going to change? It could change not at all. Here we saw it changed twice. Could it ever change once? No, right? Because we do this cyclic thing. And so if it's going to change, it has to change back. So it's always going to change for triangles twice or 0 times, in general, an even number of times. Okay, so that's one thing to notice. Another thing to notice is it seems like we're getting 0 a lot. So for triangles, it always has to change 0 times, and we've covered that possibility. or it has to change twice. And we've seen what happens when we capture alpha 1 or alpha 2. Do you see what's happening in this polynomial? What are these terms becoming? They're becoming 0 because every time we change, we might pick up this one, but we have to pick up at least one of these other two, which forces that AXC to be 0. Okay, so in fact, we can write down what is well, what did this first line give us? It gave us 1/2, but we got it for two different things. I'll say more about that in a second. And then AXC was just 1 cosine t, and all the rest of these were 0, right? And then we have minus sine of pi over 7 product of 3 sines. Okay, but do you notice anything there? Both of these sines, right, sine pi squared 2 times pi over 7, sine pi squared 2 times pi over 63, when we think about what those equal, we see that this just becomes, what is it, 53. I simplified. 70 pi. Right, we just get a positive sign, 70 pi over 361, if you think about what those signs are. Okay, that was PT1 of t. Here, what really matters is kind of the number of sign changes and where they are. And I can put these together because they're happening in the same way for both of those. And so that's why I group them, and then the 1/2 just becomes a 1 because you always get pairs. Okay, so that 1/2 isn't really important. Okay, I'm now going to give you about 1 minute to think. What can you tell me about PT2 of t? If you start doing the same, you could set up your table, start doing the same computation. What's happening with PT2 of t? It's the same thing, right? Because these are different angles, but they still have a form that's going to force us to get zeros, okay? So congratulations, you just worked out that what? That the characteristic polynomial cannot distinguish between these two triangles. It's a trigonometric polynomial in T, right? So yeah, does it look like a polynomial your students would expect? No, but okay. So characteristic polynomial is not enough to distinguish among triangles. Correct. I mean, I think if you compute, if you do numerics on them, they're not gonna. Okay, so it looked pretty awful when I wrote it down. Maybe at this point, since you did some computations and now you have an example in your head of two things that have the same characteristic polynomial, you're becoming a bit doubtful about its utility. So I'm going to convince you otherwise. Okay, so this is a useful thing. So a couple things to notice first. Yeah.
You picked the angles very carefully.
Yes.
Say
triangles. So this is we have a result in our previous paper about triangles. Sometimes, depending on the restrictions you put on your triangle, sometimes you get unique determinations, sometimes you get up to 2 possibilities. It depends. Okay. Let me give you a generic result though, because I think you're sort of thinking, well, for mode, right? So let me give you a generic result. But let me just point out first, what were we exploiting, right? You could tell I picked those angles really carefully. So we lose information in p omega of t. What you saw very clearly, I hope, in that example is when you have odd angles, which is angles of the form pi over 2m plus 1, where m is a positive integer. You would also lose information. We didn't really see it, right, in this example, but that c dot L term. That c dot L term could be the same in different scenarios if some of your L's were the same, right? You could get cancellation. So if c dot L equals 0 for some c, okay? So these are situations that seem to, give us less from this polynomial. If these things, and here I'm not being completely precise, if these things don't happen, we'll say the polygon is called admissible. That's not the precise definition of admissible, but it's good enough for our purposes, okay? So if we don't have these cases, then our polygon's admissible. Okay, so I'll give one result from the older paper. So we showed if omega is a convex admissible n-gon, with all angles obtuse, then omega is in fact uniquely determined up to congruence within the set of all convex n-gons. And I should say uniquely determined by this characteristic polynomial. Okay, so if you know you have all obtuse angles, nice things happen. You get recovering the geometry completely, right? Unique determination.
You need to know, let's say it's a triangle.
You need to know, well, it can't be a triangle, right? But it's the number of vertices. Yeah. So yes. So there are results about distinguishing whether you're an N or something bigger, but here you need to know that you're an n-gon. Okay, but many polygons that you might care about are not admissible, right? Admissible is a genericity condition. There are results when you know things are admissible, but many polygons are not admissible. So our focus in this paper was on non-admissible things. So thinking back to that historical quick overview I gave at the beginning, things you might care about, for example, are regular polygons, right? Those are definitely not admissible. What can you say in the case of regular polygons?
But a quick question, this characteristic polynomial, can you define it for a general smooth? You say some convex domain? Or is it very special? Do you need it to?
If it is a smooth convex planar domain, I'll tell you what it is. I'll tell you what it equals.
But the degree goes to infinity, or here there seems to
No,
be
the degree is 0.
Yeah, it's just the definition also works.
You probably have addressed this, I probably missed it. But does the spectrum of the Dirichlet-Neumann operator determine this?
This polynomial, yes. Yes. Okay, so So within the class of regular n-gons, each element is uniquely determined by the characteristic polynomial. Okay, so that's not as nice as the result I told you for the Laplacian, right? This says you have to be within the class of regular n-gons, but it does get at the question of you don't need to know n to start with, right? Now if you restrict in a different way, if you restrict to the class of all regular n-gons, I can tell you if you have the square or the equilateral triangle or the whatever, okay? So it does not, you don't need to know the number of vertices. Okay. It's a lot of initials. I'm not going to write them every time. Okay, so let me give you a couple more results, and we're very close to the question of smooth and hearing corners. Okay, so within the class of convex quadrilaterals and triangles, so again here I'm trying to do something where I don't fix n to start with. I allow n to be 3 or 4. Okay, so within the class of convex quadrilaterals and triangles, each rectangle is uniquely determined Okay, and here I should point out that in 2019, right, Alexandre, you had work with Savo, Lagasse, and Poltarovich that said that if you look within the class of rectangles, each rectangle is determined. So we enlarged that to say don't just look within the class of rectangles, look within the class of convex quadrilaterals and triangles, and you can pick out the rectangles uniquely. Okay, so in particular, you get the square. But what about triangles? The equilateral triangle is uniquely determined among all triangles watch out, there's audience participation coming up again, is uniquely determined among all triangles So let's think about the equilateral triangle for a second. What are the angles? Pi over 3, pi over 3, pi over 3. They're all odd, right? So what's going to happen? We're not going to have any of those cosine terms, except we will get that same term from when we have plus, 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 or minus, minus, minus. And then we will get the product of signs, but when you do that for pi over 3, you just end up with plus 1. Okay. And just to give you a sense for the proof, you sort of do it in cases depending on whether there are 0, 1, 2, or 3 odd angles. And the equilateral triangle is the only one with 3 odd angles, right? So then you can distinguish it. Because those cosine functions tell you how many odd angles you have, right? By how many of them appear, you can figure out how many odd angles you have. Okay, so note, let's get back to that question in the title. If I have a smoothly bounded domain, its characteristic polynomial looks like a lot like the one for an equilateral triangle, just with a sign change. So it turns out that some of the things we proved about distinguishing equilateral triangles from other things are, it's not hard to show that those proofs carry through to distinguish smooth domains, smoothly bounded domains, from those same things. Okay, so no, but according to the authors, they had this in mind when, it's not in their paper, but they had this in mind when they wrote down the characteristic polynomial, and it still works.
The definition you gave was for curvilinear polygons.
Correct.
So you could have a vertex where the angle
Pi, except in theirs, they restrict to angles less than pi. I didn't say that, but they, for technical reasons, they say that they restrict to angles strictly between 0 and pi. In theory, they think it's probably just due to the proof techniques. They don't think it really matters, but
I mean, the definition goes straight across and gives you that in the case.
it does in the case of, yeah.
Also to non-convex?
I don't know. We were focused on convex, so I haven't thought about that. Okay, so this similarity was sort of what got us started on asking, well, can you hear corners? Because we could distinguish the equilateral triangle in some nice cases, and our proofs went through. Okay, all right, so where are we now? We're trying to figure out which classes, hopefully all, but for which classes can we say, oh, polygons in this class cannot have the same characteristic polynomial as cosine t minus 1. Okay, so our question at this point then we have okay, so it's not exactly the question in the title. The question in the title was about Steklov spectrum, but Steklov spectrum gives you p omega. Correct, and I don't plan to. That's like many pages of through the quasi-eigenvalues. There's this, like I said, algorithmic reconstruction, but I'm not gonna explain why. Somewhat, yes. Okay, so theorem, same people, which you can probably guess. So no okay, so no triangle or quadrilateral can have the same characteristic polynomial as a smoothly bounded domain. So that would lead you to think, what happens for higher numbers of sides, right? And I'll just tell you a couple things. What happens when you assume that your characteristic polynomial is cosine t minus 1? If you think about it, that means that lots of those cosine terms had to just go away, right? They either had to go away in the sense that L dot C equaled 0, so that the cosine term got collapsed into the constant term, or they had to go away because you had odd angles, right? There are sort of length considerations and angle considerations that could have made them go away. So, proposition. Let omega be a convex n-gon with p omega of t equal p smooth of t. Then the size of L star of omega, you don't know what that is, I know, is at most 4. Okay, this is something about the lengths, okay? This is something about the lengths. So it's saying that something about the lengths has a pretty restrictive bound no matter the n. Okay, so let me tell you what L star of omega is. L of omega is the set of all edge lengths of omega with multiplicity. And for L star of omega, you take sort of the primitive ones, is how I want you to think about it. So it's the elements of L omega that cannot be expressed as the sum of two or more smaller elements of L omega. Without multiplicity. Okay, so I'm going to do an example. Yes. Okay, so quick example. So if L omega is 1/16, 1/8, 1/8, 3/16, 1/4, 1/4. Okay, should we put in 1/16? It's the smallest, right? So yes. Okay, 1/8. Can 1/8 be expressed as the sum of two or more smaller elements? No, so 1/8 should go in there. Okay, what about 3/16? Should 3/16 go in there? No, because it's the sum of 1/16 and 1/8. Okay, so 3/16 doesn't go in. 1/4, 1/4, 1/8 plus 1/8, so 1/4 doesn't go in. So this is L star, right? It's somehow catching the things that, I mean, I think of them as, sort of like prime numbers, right? It's catching the things that are really basic to all the lengths of the edges in your polygon, and it's getting rid of the rest. So going back to the proposition, again, it says no matter what your n is, if you're going to have the same characteristic polynomial as a smooth domain, you can have at most four things in here. We have stronger bounds on L star for particular n, up to I think 8, right? But in general, for a general n, that set is at most size 4.
Easier results to pass is to say that if your polygonal domain has side lengths which are incommensurate, then it's not going to be smooth.
Right. Yes, exactly.
That's sort of, I mean, that puts you back in the admissible category, and there are things, but yes, that might be, that's an easier way. This is a bit stronger in general, right? Okay, so we also...
Is there some sort of intuition undergoing?
Yes, so what you're playing with a lot of these results is when you know that your characteristic polynomial has so few terms, so many things have to cancel in that big long list of cosine, xi dot L times t. They either have to cancel or go into your constant term. And those cancellations sort of send you to this. Another way to think about it, so we also have restrictions on angles, or we have restrictions that say either this angle thing has to happen or this length thing has to happen. Okay, so it's this interplay between the angles and the lengths. So we don't have an answer, so I'll finish with our conjecture. I haven't shown you, of course, all of our results, but based on all of those, we think that a convex polygonal domain and we're not even going to stick to characteristic polynomial here. We call it bold in the paper, but cannot be Steklov isospectral to a smoothly bounded. I mean, we have things saying, you know, this has to have two even angles and they have to be opposite parity where I haven't defined even angles, but there are so many restrictions that it feels like this should be true. We're not to the point of proving that. There, I don't know. So one of the techniques we use in proving this is we sort of erase an odd angle and we replace it by an edge that is the same length as the two angles that met at that odd vertex. And we can say nice things about the characteristic polynomial relating those two things. Because you sort of made something disappear that wasn't really contributing anyway, right? Because those odd angles make things go to zero. And so we actually are working with curvilinear polygons in a lot of our proofs, even though you don't see that in what I presented. So, but I don't know. I'm not going to...
I'm confused. Your polygons are curvilinear or real polygons?
Here they are, what we worked with when I stated something like quadrilaterals, they are straight-sided polygons. However, in the proofs, we often have to pass to curvilinear polygons.
The results are about polygons.
The results are about polygons. However, the characteristic polynomial is about curvilinear polygons. So we can pass to that class when needed for the proofs.
I suspect that this is correct. And the thing is that this closed spectrum pops up in the optics, in theory of photonic crystals. So we played with those a lot, and I hazard stronger conjectures that even the highest term of spectral asymptotics is different when you have corners. And the reason is that it's like a Neumann goes up to the smaller order of square root of 1 less.
Right.
What we discovered is that when you have corners, you have to consider sometimes differential operators along the boundary of higher order, which completely changes highest order of spectral asymptotics. And numerically it's confirmed. So I suspect that even the highest term of spectral asymptotics already prohibits this. I can tell you later.
Okay.
Is this the end of the talk?
Yes, sorry. I'll stop you.
Any further questions for him?
If you, instead of taking delta u equal 0, you take,
One or
say,
something.
minus delta u equal lambda u, are there results to consider other?
I haven't seen results of this type for that situation. That doesn't mean they're not there. I maybe don't pay attention to them very well, but I haven't.
I think Jeff and his students are advertising it in talks.
Advertising it in talks, okay. I haven't seen a preprint. I haven't seen a preprint.
But they encourage it, right? Jeff's talk about that.
Right.
They advertising?
Like Helmholtz version, right? Similar results, but
So they have to redo the, I mean, not this part, but the part where you get the polynomial.
Yeah, the characteristic polynomial.
Do it a different way, better in some sense.
Okay.
They call it better.
Okay. Okay. And do they have inverse results yet, or have they?
I don't think they're planning.
Okay. What I suspected based on.
I think they're going to be happy with it.
They got the polynomial.
For
And
them,
they,
that's the
right, right.
Any further questions?
For regular polygons, if instead of the full spectrum you would know the perimeter and sigma 1, wouldn't this be?
Perimeter and sigma 1. For regular. Oh, probably. Yeah, because you could, I mean, the proof is very short anyway, but yeah, that seems to give it to you. Because you know when the lengths are 1 over n, right? And so, yeah.
There was a question before about intuition of this. Do you have an intuition about the actual eigenfunction that have a special behavior of this?
I've been thinking about eigenfunctions a bit lately, and so the answer is, in general, no, although, yeah, I'll say no. As a general statement, I'll say no, not yet.
Thank you.
Any further questions? If that's not the case, let's thank Emily again.